Okay, so we are now going to start preliminary notions with which topics in algebra starts. We left it out, we did not leave it out completely. We have actually gone through the section 1.3, which deals with the set of integers and its properties, but we are yet to go through the first section and the second section. The first one involves set theory and the second one involves functions. So in the beginning there is a discussion, and where the author says something about the subject algebra itself. We are not going to go through that discussion. Instead, we will come back to the discussion when we start group theory. That will be more appropriate. Okay. Now, we already know about set theory. We have many videos. We have gone through two different approaches to set theory. The first one that we did is naive or intuitive set theory, and the second one is axiomatic set theory. Now, in naive set theory, what we know as set in ordinary life is the definition. That is, in ordinary life, by a set we mean a collection of objects, and in naive set theory that itself is the definition. They just throw in that extra condition that it has to be a well-defined collection. That's all. We have actually seen many things in naive set theory in the videos. If you want, you can watch them. Now the thing with naive set theory is that at one point we come across something known as Russell's paradox, namely a situation where a collection is so large that the basic, what can I say, the basic rules of set theory start to break down. It cannot be called a set. We have actually come across one such collection which cannot be called a set. Not because it's not well defined, that's not the question, but because of something else. So to get rid of that situation, we developed axiomatic set theory. We in fact introduced something called the axiom of regularity to get rid of Russell's paradox. Now the point here is that the set theory that now we are going to see in Herstein's book, that is naive set theory. Okay, we are again going to see those same things which we have already gone through them once, but now we are going to look at naive set theory from the point of view of this book. The question is, why naive set theory and why not axiomatic set theory? Because if see clearly, axiomatic set theory, if you have been following those videos, is more systematic. It answers everything perfectly. It in fact also gets rid of Russell's paradox, and everything is so systematic and axiomatic. You can call upon the axioms and prove everything from scratch. There is no question of confusion anywhere. You know exactly which collections are sets and which collections are not allowed in set theory. But the thing is that axiomatic set theory needs a lot of effort to develop. In fact, although we have by now we have seen many things in axiomatic set theory, but we are yet to see many more things. We have not in fact got even finite sets. We have to develop those theories, and then at one point we will get to infinite sets, and we are yet to see the axiom of choice. So those things are still there. That is one thing. And the other thing that is more important is that we don't really need axiomatic set theory in this book. Why? You see, Russell's paradox and problems like that, they arise when the collection that we are considering is extremely large. so large that the rules of set theory start to break down. That sort of collection we will never come across in this book. In ordinary areas of mathematics, we deal with collections that from the point of view of a set theorist is they are extremely small. Of course, we deal with infinite sets all the time. Most of the times we deal with infinite sets, like the sets of real numbers, the set of real numbers, the set of natural numbers. Even these sets that we get at the very beginning, they are infinite sets, but still they are so small from the point of view of a set theorist. So naive set theory is enough for us in this book. You can think of this the difference between these two like the difference between Newton's theory of gravity and Einstein's general theory of relativity. Newton's theory of gravity works in most of the ordinary situations, but there are some cases where it fails if the speed is too large. Those of you who know about these things from physics, they can understand. So it's like that. This is like Newton's theory of gravity. It works perfectly well in ordinary situations, and this is like Einstein's general theory of relativity. We need this, but not right now. Okay, so that's why the author says that we are not going to, when the first section, when the first section starts, the author says that we are not going to give a formal definition of a set, nor shall we try to lay a groundwork for an axiomatic theory of sets. Instead, we shall take the operational and intuitive approach that a set is some given collection of objects. So that's all. And that will be enough for us. So we are going to start with some remarks about notation and terminology. Well, the treatment that we have of everything, not just set theory, in Herstein's book is very casual, sometimes to the point that we start to get wrong results. That much casuality I don't like, really. This is only the only point that I don't like about this book. Everything else is excellent, especially the problems. Okay, so we begin like this. These are some things that you all probably already know. Let us just again go through them. The statement means A is an element of the set S. Just like that, this statement means A is not an element of S. Okay. Next, a set A is called a subset of a set S if A belonging to A implies A belongs to S. That is, if every element in the first set is also an element in the second set. we write this or this to denote this statement. Okay, this notation is not meant to preclude the possibility that we may have A equal to S. Precludes means preventing from happening. This notation does not mean that A has to be strictly smaller than S or A has to be inside S properly, in the sense that this is say S, this is A. Now if this is the situation, then every element in A, I'm just simply drawing this diagram schematically, okay, without telling you what these circles or things mean. You just think of it like this. The circular region that I have drawn, the inside of it represents the set S. Like that, the inside of the inner circular, although it doesn't look circular, elliptical region, that represents the set A. So the situation here is that every element in A is automatically an element in S. So this is the situation that we are talking about here. If this happens, then we say that capital A is a subset of capital S. Now it may or may not happen that there is an element in capital S which is not in A. If that is the case, then clearly you can see that A and S are not the same set. This notation just simply means that every element of A has to be an element of S also. It may be the case that we have A and S to be the same set. In that case also you see that every element of A is automatically in S because they are the same thing. Okay, so that's the thing. But since we are mentioning this, we need to say what equality of sets actually means. For two sets A and B, we say that A and B are equal and write A equal to B if they consist of precisely the same elements. Naturally, because then they will be the same set. Note that A is equal to B if and only if A is a subset of B and B is a subset of A. You try to think about this, then you will see that this is the case. If A and B are the same, then automatically A is a subset of B, because you can, if you write A here in place of B, then every element of A is automatically in A, and this also becomes the same statement. So if this is true, then these two things are true. Conversely, if these two things are true, then this has to be true. Why? Okay, so if these two containments are true, then why do A and B consist of precisely the same elements? B cannot have anything different than A. Why? Because if there is an element in B which is not in A, then B will not be a subset of A, contradicting this one. Like that, because of this, A cannot have any element that is not in B. So that's why they will consist of precisely the same elements, and hence we will have A is equal to B. So while proving A equal to B, we would prove that both the relations this and this are true. That's how we prove that two sets are equal. It's a standard procedure. Okay. Okay, proper set. Yeah, proper subset. If A is a subset of S, so when from now on, when we see this, not this statement of course, because we also have equality of other things, right? Numbers besides sets, vectors, many other things. But this symbol is specifically between two sets. It will appear only between two sets. So when you see this symbol, or this one, where is that other one? This one. Then it automatically means that A and S are sets. So if A is a subset of S and A is not equal to S, then we say that A is a proper subset of S. Although Herstein does not write any symbol for denoting proper inclusion or proper subset, we are going to write like this. We denote this by writing that is, A is a subset of S, but it's not equal to S. Okay, so we are going to use this symbol. Don't confuse between this one and this one. Okay, this means A is not a subset of S, and that means there is at least one element in A which is not in S, because if every element in A is also there in S, then by definition A is a subset of S. In this symbol, you just write the usual subset symbol, then below that you draw a horizontal bar and strike it out. Okay, so that is our symbol for proper subset. Then there is of course the question of empty set. There exists a set consisting of no elements it is called the null set or the empty set. and is denoted by this symbol. There is a difference between this symbol and the Greek letter phi. Okay, in phi, this elliptical thing, this region, it is like it's more horizontal than vertical. Actually, to write the symbol for empty set, you write 0, like just how you write 0 ordinarily, then strike this. Okay, it's not phi. And after that, there is of course this notational remark, the thing that you know, those of you who know about set, I mean all of you know, we have gone through this in school. So that is the set builder notation. If S is a set and PA is any property that an element A belonging to S may or may not satisfy. Then by this notation, we mean the set of those elements A in S that satisfy the property, that is for which PA is true. PA is some property that depends on the element A. It is in terms of A. Say for example, if S is the set of all integers and PA is the statement that A is an even integer or A is a positive integer, then there is that question of PA being true or not. So this set will denote the set of those integers that are, say, positive. Okay, in fact that is the example that we will take to excuse me, understand this situation. For instance, if S is the set of all integers and PA, or we can instead of saying about PA and A is the set of all positive integers, then using this notation we can describe A like this. It is the set of those A in S such that A is greater than 0. Okay, this symbol denotes such that, this vertical bar. Okay, but I am not going to use vertical bar. For some reason I don't like this. Instead, we will write this. I will use colon in place of this, or let me write it more generally. There is one other example also. Let me write that one also. Let S be the set consisting of the objects Okay, so there are some 10 objects which have been numbered like this. There may be any objects, and S is the set consisting of these objects. Let A be the set, or let A be the subset, or let us just write set. Let's not confuse you at this stage itself. Be the set consisting of then we can describe A as this. A is the set of those objects in S such that I is equal to 3n plus 1, where n takes these values 0, 1, 2 and 3. You can see if you put n is equal to 0, you get I equal to 1. Putting n equal to 1, you get I equal to 4, then 7, then 10. Okay. It doesn't, Herstein doesn't say that this is set builder method of, or rule method of denoting a set. He doesn't mention those things at all. Okay, now after that we have combination of sets. We can, just like two numbers can be combined, or several numbers can be combined using the operations that we have available to in the set of numbers, ordinary addition, subtraction, those things. Like that we can combine sets also, and the first operation that can be used to combine them is union. Traditionally it's the first, but you can of course start with anything, I mean any one of these, the four available. So this is our definition of union. Let A and B be sets the union of A and B denoted by this symbol. Is defined to be the set of those elements that are in A or B. Now there is something about this word OR. It's known as the inclusive OR. As opposed to the exclusive OR. Inclusive OR means, okay, let us first see what exclusive OR means. Exclusive OR is the connective which is used in a situation where something happens or something else happens, but both of them cannot happen simultaneously. That is exclusive OR. Whereas inclusive OR means either this can happen or this can happen or both can happen. Okay, so we have to write it here. Here X belongs to A or. The fact that I am saying many things but not writing them fully is because all these things I have already described and we have discussed in our videos on knife set theory. So here we are being somewhat sketchy. We are not writing everything down. You can go and watch those videos, you will get everything there. Here X belongs to A or X belongs to B means either X belonging to A is true or X belonging to B is true, or both X belonging to A and X belonging to B. I should perhaps write them within quotes. It denotes the fact that these are statements. Are simultaneously true. Okay, so now let us take some examples of unions. For any set A union A equals A. Why that is the case, you convince yourself. You look at the definition and see why A union A is equal to A. If A is a subset of B, then A union or it doesn't matter, but let us take it the way it is given in the book. Then A union B equals A. The union of two sets, one of which is contained in the other, is the bigger set. Okay. If A is this set consisting of these three objects, x1, x2 and x3, any three objects, and B consists of these objects, y1, y2, x1, then A union B equals x1, x2, x3, y1, y2. One more example. If A is the set of all blonde-haired people who have that golden kind of hair, and B is the set of all people who smoke